Physical changes. We should first be clear about what is meant by physical changes, so a definition is in order. A physical change is a change in state or form that does not produce a new substance. Changes in state are already well known, and I'll return to them in a moment. But right now, I want to concentrate on what is meant by a change in form. Here is the first example of someone ripping paper. The form of the paper has now changed. It's in two pieces. However, no new substance has been formed as a result. That is why we call this a physical change. Here is a second example in which a wine glass is being crushed. The form of the glass has been changed into little pieces, but no new substance has been formed. So this is also a physical change. A third example is shown by this little girl who's crushing a can. The form of the can has been altered, but no new substance has been formed. Our final example shows a walnut being crushed. This is a physical change because the form of the walnut has been altered into pieces, but no new substance has been formed. So these are examples of changes in form. Let's now look at examples of changes in state. The most common one is the melting and freezing changes in state, since the same substance which is melted can also be frozen, and frozen substances can be melted. We often say that this is a reversible change. In the first example, we see ice melting to form liquid drops. This is a physical change because it's a change in state, and as previously mentioned, no new substance is formed. This is what is common between changes in state and form. In both cases, no new substance is formed. In our second example, this person is about to throw liquid water into the air. It's so cold that the water droplets in the air will freeze quickly enough to become small ice particles before they hit the ground. In this next animation, we see a model of what happens when liquid water freezes and turns to ice. You'll notice that as the molecules slow down, they arrange themselves in a pattern in which spaces or holes are created in the ice. It is these holes in ice that make it less dense than water, which explains why ice floats on water, as we all know. But it also shows that as water turns to ice, the creation of these holes means that the volume of ice formed is now greater than the water from which it came. For example, if you start out with 10 cups of water and freeze them, you'll end up with 11 cups of ice. So the volume of ice expands about 9% over the volume of water. This has a few consequences. For example, here are two examples of outdoor piping used for water hoses. If water is not drained out before the freezing weather sets in, then water can expand with such force that it will burst the pipe. Let's now look at vaporization and condensation. I'll focus first on vaporization from liquid to gas. These water pools are called salt evaporation pools and are made to obtain sea salt by evaporation of seawater. They're found all over the world. Evaporation is a slow and invisible process. Vaporization in the form of evaporation is a key step in the water cycle. Here, evaporation allows for the transfer of water from oceans, lakes, and rivers to the atmosphere. When vaporization is rapid and visible, as shown in this pot, we call it boiling. So boiling and evaporation are both forms of vaporization. One is fast and visible, one is slow and invisible. Now let's look at condensation. Here's a condensation of water vapor, which is a gas, on a cold window. When water vapor touches a cold enough window, the gas will condense on the surface to form liquid droplets of water. In the water cycle, the evaporated water from lakes, rivers, and oceans rises up and meets colder air, where it then condenses into small liquid drops to form clouds. Now let's look at sublimation. I'll remove these arrows to keep the diagram looking cleaner. The sublimation from gas to solid is also known as deposition. This may not be a widely used term, but you should be aware that when you see it or hear the word deposition, it's simply the form of sublimation from gas to solid. Deposition means that the solid is being deposited onto the surface. The most common example of the change from solid to gas is dry ice, which is solid carbon dioxide, shown here at very low temperatures. The white wisps that you see are not carbon dioxide gas, which is invisible, but rather tiny droplets of liquid water, which resulted from the cold carbon dioxide gas cooling the water vapor in the air until it condensed to form tiny droplets of liquid water. The next clip shows massive amounts of white clouds forming when somebody dumps large amounts of dry ice into a swimming pool. Again, the white clouds are tiny droplets of water, but there's also carbon dioxide mixed in with that, and since carbon dioxide is denser than air, it helps drag the white clouds downwards. Now, going the other way, from gas to solid, here's a picture taken in my backyard of frost on branches of a tree and the top of our gazebo. Overnight it was very cold, so that when the water vapor in the air touched the cold branches or the wood, it changed directly into solid ice. Trees and power lines covered in frost are a common winter scene, a result of sublimation. Although I have really emphasized state and form with these examples, there's one more important concept to add to this definition, and that is reversible. You already know something about what can be reversible. For example, a jacket can be reversible, or a balloon can be inflated and deflated, inflated and deflated. This is a reversible action. What do you think may be reversible in this definition? You probably would say state and form, and you'd be correct. Since both are changes, we'll say that the change is reversible. So let's take the word from the banner and slide it into the definition and place the banner up here. Now, it's fairly easy to understand that all changes in state are reversible. We're familiar with most of them. Here's one example involving molten iron changing from liquid to solid. Okay, the video was stopped before we could see the solid, but you know it was going to happen. But when it comes to a change in form, like ripping a piece of paper, how is this reversible? Well, in theory, you could take the pieces and glue them or tape them back together. This may work with two large pieces, but seems impossible with shredded paper. The point is that the atoms and molecules in all the pieces are still the same as when they were in one piece, so nothing has changed. If the pieces became different in some way, like changing their structure, then that would be called a chemical change. Speaking of shredded paper, here's a clip showing how technology can make it happen, at least for paper.
Is it possible to reassemble documents that have been sliced and diced by a shredder?
This is the confetti. This is the, are you kidding me? This is not the fun moment for the special agent.
The answer is yes. There's actually software that reconstructs shredded pieces after they've been scanned onto a computer.
Now let's consider a cracked egg Is this reversible? In principle, we could put the yolk and egg white back into the shell, close the two halves, and somehow seal everything back. Also ask yourself if the cracking made any changes to the molecules and atoms. None were made, so this is a physical change. Finally, let's consider popping corn. Heat is added to the kernels, causing the moisture inside the kernels to turn into steam, which expands and explodes the kernels into 20 times their size. Let's look. As mentioned, the moisture inside the kernel turns to steam as it absorbs the microwave energy and then explodes the kernel. But before the explosion happens, some of that steam escapes, and as it hits the inside of the bowl, it condenses because the side of the bowl is a little cooler than the hot steam. You can see a band forming there in the middle, which is the condensed water vapor. This sound is the microwave. I'll speed it up now 4 times. This is still a physical change as no new substance has formed. However, I can't see how, even in principle, the puffed corn can be changed back into kernels. So here's a physical change that is not reversible. An example like this may be rare, but since it exists, we should probably say that almost all physical changes are reversible. This ends the video on physical changes.